In this lesson, we're going to talk about calculating stopping distance. So, the implications of physics principles while driving. So, one of them is headlights. So, headlights allow us to see farther ahead of the vehicle in the dark. And conventional headlights allow a driver to see about 60 meters ahead. But at highway speeds, this typically does not give the average driver enough time to react, which is why a lot of animal collisions happen in the dark. Now, new HID headlights allow a driver to see up to 100 meters ahead of them. However, they're dangerous for drivers in oncoming traffic because they're very glaring. So, pros and cons of both of them. So when we look at different physics questions we get when driving, one of them is going to be about merge lanes. Some are based on the speed limits of two roads, residential roads versus highways. And we use the displacement formula to calculate the length of a merge lane needed to accelerate from one speed to another. So we can also inquire about yellow traffic lights. The higher the speed limit on a road leading up to a traffic light, the longer the yellow light will have to be in order for drivers to safely slow to a stop. So to do this, we need to look at the stopping distance of a car. The stopping distance refers to the distance between a vehicle and the need to come to a complete stop. And this is made up of two separate distances, the reaction time and the braking distance. And distance goes by as we're reacting. To calculate the stopping distance, there are 4 steps. One is reaction distance. So reaction time can vary from person to person and can be affected by cell phones, passengers, loud music. And the average reaction time for drivers is about 1.5 seconds. Reaction distance is how far the car goes during the time between when the driver identifies the need to stop and starts applying the brake. Since the vehicle typically is traveling at a constant speed, we use the formula velocity multiplied by reaction time to get the reaction distance. So, for example, a car traveling at about 20 meters per second, or roughly 10 kilometers an hour, over the limit. When the driver sees a pedestrian on a crosswalk ahead, the driver has a typical reaction time of 1.5 seconds. How far does the car travel before the driver reacts? So to calculate the displacement, we're going to take the velocity at 20 meters per second, multiply it by the reaction time of 1.5 seconds, and then get a total distance traveled of about 30 meters. And that's just the reaction time. Now, braking distance is how far the vehicle travels from the moment the brakes are applied until the car comes to a complete stop. The typical deceleration value is about negative 5.8 meters per second squared, which allows a vehicle to safely come to a slow stop. To determine the braking time, which is going to be the amount of time needed to come to a complete stop based on the initial velocity of the car and the rate of deceleration. So we're going to use the formula for acceleration and solve for t. So we're going to rearrange this formula for the change in time for braking is final velocity minus initial velocity divided by the acceleration. But because the final velocity is always 0 because we're coming to a stop, I always put it into my calculation, so I visually have it there, but it is an unneeded number. So braking distance is based on the braking time, but how far you travel and how far you travel until your vehicle comes to a complete stop. So since the vehicle is changing speed, we know both velocities and the braking time, so we're going to use the formula. Displacement is equal to final velocity plus initial velocity divided by 2 multiplied by time. So if a car decelerates with a typical rate of negative 5.85 meters per second squared, what distance will the car travel while slowing from 20 meters per second to a stop? So we need to find out how long it's going to take. So we take our final velocity of 0, subtract our initial velocity of 20 meters per second, and divide it by our acceleration of negative 5.8 meters per second squared. And we get a complete time of 3.42 seconds. Now for step 3, we need to calculate our displacement during that 3.42 seconds. So we take our final velocity of 0, add it to 20 meters per second, divide it by 2, and multiply it by our time of 3.42 seconds. So we get a total braking displacement of 34 meters. To find our complete stopping distance, what we need to do is add the distance traveled during our reaction time and the distance that traveled during our braking time. So, example 1, looking at our stopping distance. Determine the typical stopping distance for a car traveling at 110 kilometers per hour or 30.6 meters per second. We're going to assume the reaction time of the driver is 1.5 seconds and the deceleration is negative 5.85 meters per second squared. So, step 1, calculate the reaction distance. We take our velocity, 30.6 meters per second, multiply it by our time, and get our total stopping distance of 45.9 meters. Step 2, calculate our braking time. So we take our final velocity of 0, subtract our initial velocity of 30.6 meters per second, and divide it by our acceleration of negative 5.85 meters per second squared, giving us a total braking time of 5.22 seconds. We're going to determine the typical stopping distance for that car. So this is once the brakes are applied, we need to now calculate the braking distance. So we're going to take our final velocity of 0, add it to our initial velocity of 30.6 meters per second, divide that by 2, multiply it by our total braking time of 5.22 seconds. Then we get our braking distance of 79.8 meters. Now to determine the stopping distance, we have to add those two distances together. Our reaction distance of 5.9 meters added to our braking distance of 79.8 meters, and we get our total stopping distance of 126 meters. So that is how long it takes to brake when you see an obstacle at 100 kilometers an hour with the average reaction time of 1.5 seconds. Or 1.5 seconds. Okay, one more example. A driver with a typical reaction time of 1.5 seconds attempts to brake on the ice, causing his deceleration rate to reduce to negative 4.32 meters per second. So now what is the minimum stopping distance if the car is traveling at 20 meters per second? So again, step 1, calculate our reaction distance. So we're going to take our initial velocity of 0, subtract our final velocity of 0, subtract our... We're going to calculate our reaction distance, our braking time, and then our braking distance. And then we're going to add those two distances together. So our reaction distance will be our initial velocity at 20 meters per second, multiplied by 1.50 seconds, giving us a total reaction distance of 30 meters. Much shorter than when the vehicle is traveling faster. Our braking time, we're going to take our final velocity minus our initial velocity, so 0 minus 20, and divide that by our deceleration rate of negative 4.32 meters per second squared, giving us a total braking time of 4.63 seconds. To calculate our braking distance, we're going to take that time we calculated at 4.63 seconds and multiply it to our final velocity plus our initial velocity of 20 meters per second divided by 2, to get a total braking distance of 46.3 meters. Lastly, we're going to add those two distances together, our distance traveled during reaction of 30 meters and our distance traveled during braking of 46.3 meters, and we will have a complete stopping distance of 76 meters. So that is how you calculate stopping distance. It involves the the distance traveled during reaction, calculating the stopping time during braking, and then the distance traveled during braking.